ladies and gentlemen. Welcome you here at the Technical Forum of the Group Exhibit Hydrogen Fuel Cells and Batteries in Hanover 2014. Please come in, have a seat, have a drink on the house and enjoy with me our next presentation here on stage, dealing with the topic SOEC development status at Sunfire GmbH. And your presenter is the project engineer from Sunfire, Dr. Christian Walter. Give him a big hand.
Thank you for the kind introduction. What was written on the screen is actually wrong. It is not SOFC development, but SOEC, as you were told, so it's on the slide was wrong. As I said, thanks for the introduction, and thanks for the ability to show you some development status that we have at Sunfire now. Good afternoon, ladies and gentlemen. I will first start with a short outline on the talk. First of all, I will give you some brief company facts from Sunfire, what our vision is, what the company portfolio we already have in our portfolio is. Then I will go on to show you something about the SOEC motivation, which is related to power to liquids. I will show you why we want power to liquids and why we need a high temperature electrolysis for this, or why we want high temperature electrolysis for this. And I will then, the main part of my talk will be on the Sunfire project, which is actually the project where we are developing the power to liquid technology and therefore also the high temperature electrolysis. I will there show you some recent results from the material development, some system tests, and also the recent status of the SOEC module that we have in development. First of all, some company facts. Our vision. So the vision Sunfire has is closing the carbon cycle. This means that we want to produce renewable fuel. This is sketched up here in this graph. This is what we call the carbon cycle, and on top here you have fuels, which can be gaseous as well as liquid, which could be, for example, natural gas, petrol, kerosene, some chemicals and things like that. And on the right side you have the electricity generation. So what we do is using the fuels to generate electricity or also heat, or use it for mobility purposes. And this is where we at right now. So we are using all the fuels to generate electricity, heat and mobility. This has the great disadvantage that we have an exhaust gas of CO2, which everyone knows is unfavorable because of climate change and things like that. So the idea we have at Sunfire is to close this carbon cycle. This is what is shown on the left side. It's called fuel generation. So what we do is we use electricity from natural sources, green sources like wind energy or something like solar energy. And this electricity is then fed into this carbon cycle. We use carbon dioxide as an input for this process. And by using techniques called power to gas or power to liquids, we are able to generate fuels which are then renewable. And for this project, the fuel generation, we need the electrolyzer technology, because we use the electricity to generate hydrogen with the electrolyzer, and this hydrogen is then used with the CO2 to produce fuels, renewable fuels. What is also important here is that Sunfire is the key component we develop is the high temperature electrolyzer, or also the high temperature fuel cell. This is shown a sketch from our cell is inside the carbon cycle, and we use this cell as well as fuel cell, also as an electrolyzer. So the technology is the same for both sides. And this is the vision of Sunfire. Now let me give you some company facts. Sunfire was founded in 2010, and then the idea of Sunfire was what I just showed, the power to liquids, power to gas technology. And they were then looking for someone who could supply them the high temperature electrolyzer, and they couldn't find anyone. So what they did find is Staxera, a company founded in 2005, which was dealing mainly with solid oxide fuel cells. So they found together Staxera, then Sunfire acquired Staxera, and now we are developing the power to liquids and high temperature electrolyzer under the brand of Sunfire. This year, actually in January, our first financing round was finished, and we have two new investors, which is Electronova Capital, which is part of EDF, Electricité de France, and also the Total founding group. So they invested money to our company to also develop the power-to-liquids technology. Bilfinger is also part as an investor in Sunfire since last year approximately. We now have about 70 to 80 employees, most of them engineers, but also some technicians and business people. We have more than 30 patent families. We have, of course, still strong support from the government. And the revenue of Sunfire is steadily increasing. We started about 0.5 million in 2009, and last year we reached 4.1 million, so quite a growth there. And we have also customers from all over the world. So let me now give you a short information about the product portfolio we have. As I said, our main component is the energy converter, either fuel cell or electrolyzer. This is what you can see on the left side. It's called the SOEC stacks. What you can see there are 30 cell stacks, and this is the key component we have for all our modules. The second portfolio we have is the micro CHP, which is where a fuel cell is inside this module, 60 cells, and this micro CHP module generates about something like 1 kilowatt electricity and 3 kilowatt overall with heat, and can be bought from Weiland. We are working together from Weiland with this micro CHP modules. We also have a department which is doing the system engineering. So they are doing stuff like heat exchangers, heaters, desulfurizers, all the things you need for fuel cell to work, or also for electrolyzer to work. And we also right now have a project where we are producing small CHP modules with an electricity output, also fuel cells, from 20 kilowatts to 100 kilowatt system. This is together with ThyssenKrupp. Now let me come to the motivation for power-to-liquids and the high-temperature electrolyzer. The motivation why we started this project is actually that there was an EU study that showed that the demand of renewable fuel will increase to approximately 140% in the next years. This is because of EU regulations, which say that 10% of the final consumption from all kinds of transport electricity or transport mobility you have has to come from renewable sources. At the same time, the supply of renewable fuel is decreasing because you have to have at least a 50% greenhouse gas emission saving from these biofuels, which rules some of the fuels you can buy now as biofuels, which rules them out, so you have less supply. So this leads to the fact that we have a high demand and a low supply, and there, of course, there is a business case in that. Now this is a sketch of the power-to-liquids technology. As I said, we are using renewable electricity from wind or solar energy. We have then the electrolysis, the high-temperature electrolysis. Then we have a conversion to syngas, where we put the hydrogen from the electrolyzer and the CO2 from the atmosphere in. We produce syngas, which is then fed into the Fischer-Tropsch synthesis to get the fuel out. So the key part of this process is the high-temperature electrolyzer, as I already said, because the Fischer-Tropsch is a technique which has been working since, I think, 50 years or something. So, and this is the core technology for this process, and this is globally not available yet. So, and why do we actually want the high-temperature electrolyzer? Low-temperature electrolyzer are available, as you probably know, but we want high-temperature electrolyzer, and this is shown on the next slide, why we want this. Here you can see the process again. You have water, you form steam. From the steam with the electrolyzer you get the hydrogen, then the syngas, and then the hydrocarbons. If you use a low-temperature electrolyzer, you have to supply all the energy to evaporate the water to steam with electricity. But what you also have at a Fischer-Tropsch synthesis is a lot of waste heat, which is just because the process is an exothermal one. So the idea now is to get the waste heat, use it for the high-temperature electrolyzer, and use it to boil the water, actually. And so you save a lot of electricity because you can use the heat from the Fischer-Tropsch reactor. And this ends up to the fact that you have a heat recovery and an efficiency increase of about 16% to 70% with this process. this is why we want the high temperature electrolyzer. Now let's come to the Sunfire project, where we, as I said, will develop or are developing the high temperature electrolyzers and the power to liquids technology. There are two project aims, which is of course the electrolyzer, and on the other hand the conversion. And we have aims for the electrolyzer, which is the high power density, of course, to decrease the investment costs. And also we have the low degradation to increase the lifetime of the electrolyzer. On the other hand, we have the conversion. This should be a pressurized system because Fischer-Tropsch usually works at higher pressures at about 15 to 30 bar. And we also have to have a fast startup and shutdown, just because when we use volatile wind energy, for example, it would be beneficial if the system can just shut down and start up at quite fast time. We also have some partners. Carafol, for example, are developing the cells we use for the electrolyzer. IFA is a testing facility where the cells are tested. We also have the Fraunhofer ICT, which is testing a lot of materials we'll use, and also some other competence like Jülich, Universität Bayreuth, and Universität Stuttgart. The development strategy we have in this project is kind of a bottom-up one. So of course we first look at the materials we have. We look if the materials we are using for the fuel cell are also usable for the electrolyzer. And if not, we have to improve them, of course. Then if this is finished, we are going to short stack tests, which means that we have a pre-evaluation of the material combinations that we found in the material survey and development. And we just gain first SOEC development operation experience, with this short stack tests. Then we are going to the 30-cell stack, which is the key component I've shown you earlier on, the base component for all our modules. So this is the system close evaluation, and this is the first thermally stable, self-sustained SOEC operation with the 30-cell stacks. The short stack tests are done in a furnace. And last but not least, we will of course develop the SOEC module. Now let's come to some results. Here you have I've shown you the material survey and development from the metal sheet. This was done in the Fraunhofer ICT. And we had some pressure chambers where we could have pressurized oxygen and pressurized steam, and just look how the metal sheet behaves, if it degrades at a fast rate, or what happens with different materials in this pressure chamber. And they did electron microscopy and elemental analysis, and this is what you can see on the upper left is an SEM image, and on the upper right is elemental analysis of oxygen. And what you see here is at the bottom you have the metal, and an oxide layer, a protective oxide layer forms on top of the metal, which is protecting the metal from oxidation. We also have, as I said, cell development together with Carafol and IFA. There we are using a 6 scandium 1 zirconium oxide electrolyte, and those were developed at Carafol, tested at IFA, and we had shown that with the pure cell test we have a degradation of about or less than 0.6% per 1,000 hours. After those material evaluations, we did the, as I said, short stack tests. And such a short stack is shown here on the upper left, just a picture of it. And on the upper right is a voltage over time diagram. And what you can see that the blue curve is the current. The current is always constant. Besides, it's stepwise, but if you have a steady state operation, the current will be constant. And the other graphs here are the voltages. So as you see, for example, here at a steady state operation, at steady current, you can see that the voltages are increasing, and this is because of degradation of the cell. But you can also see that the degradation is only in the beginning, and afterwards, after some time, you have quite a steady voltage, so the degradation is only at the beginning. We have not yet fully understood actually why we have a systematic degradation at the beginning, but for the steady state operation, this doesn't make it's not that bad. Of course, you decrease the initial power of the stack, but for the steady state operation we have degradations less than 1% in 1,000 hours. And we also did 3 short stack tests with overall 4,500 hours SOEC operation, and we also could increase the power density from stack to stack. Now let's come to the 30 cell stack, which is, as I said, the first part where we really did the stack tests in a thermally self-sustained environment. And also this is, as I already have said, the key component of all our modules we have. And we also tested different operation modes and operation strategies with this stack. Just one more information, this stack, the 30 cell stack, was first operated as a fuel cell and afterwards as an electrolyzer. This was mainly because we also wanted to get some information about if we can really use one stack as a fuel cell at the one hand and just change the in gases and use it as an electrolyzer kind of reverse mode. And this is really possible with this stack. And what you can see here on the left side is the curves of the SOFC, of the fuel cell operation, and on the right side is the electrolyzer operation. And the SOFC test already showed that with such a stack we can have a power of 1,200 watts from 30 cells, which is a performance record for sunfire so far for the technology we use. And by changing it to SOEC mode, we can even get 4,200 watts, so it's 3.5 times the power than we have in the fuel cell operation. This is mainly because we have higher voltages in SOEC mode. And even we did it like at a current of 100 ampere, and even the current collector started glowing at this time because we just had to we were using the same current collector we use for the SOFC mode, and that was just probably too low. So for the next test we have to exchange the current collector for this stacks. So this was the power density. So we reached quite a good power density with this electrolyzer. So the first aim of the project is finished. Now let's have a look at the degradation of the stack. And what you can see here is, as I said, we have different material combinations in this stack. And this is what you can see here. This is a steady state operation, and you can see 4 different regimes how the materials how the materials behave over time. And you can see that the degradation, as I said, the higher the voltage, the higher the slope of the voltage, the higher the degradation. And we have, if you combine all of these, we have a degradation of about 1.6% for 1,000 hours. But the best material here, which is this one, has only a degradation as low as 0.7% in 1,000 hours, which is about 4 times better than the target. The target of the project was a degradation of 3% in 1,000 hours, so we have a 4 times better degradation right now. This stack has been working for 2,500 hours, I think, roundabout right now, and we are still testing it. So the degradation also shows really promising results. And last but not least, the startup shutdown procedure of those stacks. This was actually an emergency stop because of the test station. So this test wasn't planned because we just wanted, firstly, we wanted to show the degradation, and afterwards we wanted to do some operation regimes. But what you can see here is that we had an emergency stop because of the test station, as I said, and the current was just ramped abruptly down to 0. And afterwards we slowly ramped the current up again in 36 minutes from 0 to 600 milliampere per square centimeter. So this already shows that a hot standby mode is possible, but we will do further investigation of this if you can, for example, also do it in 10 minutes or 5 minutes. But this will take place after we have finished the degradation measurements. Now let's come to the SOEC module. This is right now under construction. The engineering is finished. This is what you can see here on the left side. This will be the SOEC module we have. These are 3 stacks, 3 30 cell stacks, so at all 90 cell stacks on top of each other. And this module, which we call the integrated stack module, as I also have shown you earlier, will then be integrated in the pressurized SOEC module, which we will then use for the power to liquid plant. As I said, the engineering is finished, And we are right now building it. The pressure vessel is already ordered. So we are about to build it. And the outlook. This is the power-to-liquid plant we are building right now in Dresden at Sunfire. This is just a CID model, and this is actually a picture taken from the plant, which has been built up right now and will probably start into operation end of this year, beginning of the next year. The SOEC module, I've shown you one slide earlier, will probably also be finished around summer. And next year we plan to couple both the processes. So we have the electrolyzer and the power-to-liquid plant. And this power-to-liquid plant will be able to have 1 barrel fuel a day. So approximately, I think, 150, 156 liter or something like this. Okay, then if you have further comments, also tomorrow I will be here at our booth at B50. And thank you for your attention.
Thank you, Dr. Walter, for this very interesting presentation here on stage. And it's your turn. Are here any questions in the audience? Not yet. Yes. Would you be so kind to introduce yourself?
Eva Ravn Nielsen, FCH Test Center, Technical University of Denmark. I'm wondering of your strategy of CO2 source for your electrolysis.
Okay. For the plant we are building right now, we are just using CO2 from bottles, actually, because we are doing it stepwise. So we just wanted to show electrolysis works, power-to-liquid works, combination works, and so we just use the CO2 just from pressure vessels that we buy by Air Liquide, I think. But we are in contact with some companies who actually want to have the CO2 from the atmosphere. But we have to check on this if we can do a project with them. But right now we are just using pressure vessels.
Thank you. See another one? So not yet. Thank you again for being here and to speak to us.
Thanks for the invitation.
Okay. So like mentioned, Mr. Walter will stay here at the group exhibit Hydrogen, Fuel Cells and Batteries until tomorrow. And he and his colleagues will be very, very glad if you come and discuss any topic maybe come later in your mind. Like written here at the flat screen, the booth is at B50 here at the group exhibit. Thank you for staying here with us and listening and watching our very interesting presentations. It's the last one for today. We are starting again tomorrow at 10 a.m. Thank you. Have a nice day.